Hello, my name is Christian Boyne, one of the authors of AVDDPG, Federated Reinforcement Learning Applied to Autonomous Platoon Control. The decentralized nature of autonomous vehicle platoons leads to challenges for real-life systems, as the training and deployment of deep reinforcement learning models is time-consuming and not guaranteed to generalize for multiple vehicles. The goal of this study was to explore FRL's effectiveness for AV platooning by designing and implementing a FRL framework atop of a custom AV platoon environment. To the best of our knowledge, no other works at the time of this study apply FRL to autonomous vehicle platoon control. Many existing works apply FRL on settings related to distributed networks, edge caching, and communications. In addition, we provide a comparison between gradient and model weight aggregation in FRL and determine the better solution. Furthermore, we define two novel ways to apply FRL to AV platooning scenarios, known as Inter-FRL and Intra-FRL. Last, we apply FRL to varying platoon lengths, analyzing the advantages as the platoon grows. What is FRL? FRL is an extension of federated learning, or FL, developed to improve the demanding and time-consuming process of training DRL models. DRL models are sensitive to small changes in hyperparameters or model parameters, leading to non-reusability of a DRL model across multiple similar agents. FRL provides advantages for AV platoons, where many similar agents would benefit from sharing data during training to build a robust model. An animation is provided showing how FRL can be applied to the AV platoon. By considering a platoon of vehicles 1, 2 to the nth vehicle, we can define the position, velocity, acceleration, control input, and length as per the below figure. In addition, using these defined parameters, along with tau sub I, the coefficient representing the vehicle dynamics, we can formulate a state space model of our system. Furthermore, in cooperative adaptive cruise control constant time headway policy models, the headway and desired headway can be used to define the position error, or EPIT, and velocity error, EVIT. Taking the derivatives of these two variables is useful in finalizing our state space formula, as we'll see on the next slide. Using the position error, velocity error, acceleration, and acceleration of the leading vehicle for a generic vehicle VI, we can define the state of the system as x sub IT. We also can provide the state space equation for the model, along with system matrices A sub I, B sub I, and C sub I. We need to provide an MDP model for our DDPG agent to interact with. We provide a discretized state along with an action and reward equation for our AV platooning system on this slide. As discussed earlier, we provide two ways to apply FRL to AV platooning: Intra-FRL and Inter-FRL. Intra-FRL is defined as a system where platoons are considered as isolated systems from each other. Intra-FRL implements federated averaging within platoons, and there is no sharing of parameters across platoons. Inter-FRL, on the other hand, is defined as a multi-platoon system where parameters are averaged amongst vehicles across platoons. There is no parameter sharing within the platoons in Inter-FRL. In order to evaluate Inter-FRL's effectiveness on AV platooning, we trained 3 sets of DRL experiments performed across 4 random seeds. First, we trained 2 platoons with 2 vehicles using no federated reinforcement learning. Next, we trained 2 platoons with 2 vehicles using Inter-FRL and gradient aggregation, or Inter-FRLGA. And last, we trained 2 platoons with 2 vehicles using Inter-FRL and weight aggregation, or Inter-FRLWA. 3 sets of convergence curves are provided on this slide, one for No-FRL, one for Inter-FRLGA, and one for Inter-FRLWA. Inter-FRLWA converges faster and also shows a more stable training, as indicated by the reduction in the standard deviation across the 4 seeds, or the shaded area in the plots. By performing simulations across the 4 random seeds for No-FRL, Inter-FRLGA, and Inter-FRLWA, it was found that Inter-FRLWA had the most favorable performance of the 3. For Intra-FRL, we use 3 sets of DRL experiments performed across 4 random seeds. First, we trained 1 platoon with 2 vehicles using no federated reinforcement learning. Second, we trained 1 platoon with 2 vehicles using Intra-FRL and gradient aggregation, or Intra-FRLGA. Third, we trained 1 platoon with 2 vehicles using Intra-FRL and weight aggregation, or Intra-FRLWA. For our Intra-FRL analysis, we provide 3 sets of convergence curves. One for the base case where no FRL is applied to the platoon. Second, the Intra-FRL-GA scenario. And last, a curve for the Intra-FRL-WA scenario. In the Intra-FRL-WA scenario, it can be seen that faster training occurs as well as more stable training across each vehicle in the platoon when compared with Intra-FRL-GA and no-FRL. Simulations are performed across the 4 random seeds for no-FRL, Intra-FRL-GA, and Intra-FRL-WA, and it was found that Intra-FRL-WA provided the best performance across the 3 scenarios. In summary, for the experiments performed thus far, it was found that Intra-FRL performed better than Inter-FRL. This is because each follower's policy depends on the predecessor vehicle's policy. Thus, the sharing of the predecessor vehicle parameters gives an advantage to the following vehicle. This advantage is not present in Inter-FRL, where vehicles in the same platoon index share parameters amongst each other. The final set of experiments in this study consists of 2 sets of 12 DRL experiments across 4 random seeds for variable length platoons. First, we train 1 platoon with 3, 4, and 5 vehicles using no-FRL. Next, we train 1 platoon with 3, 4, and 5 vehicles with Intra-FRL-WA, which was previously identified as the optimal aggregation strategy for FRL applied to AV platoons. 3 sets of convergence curves are plotted comparing Intra-FRL-WA to no-FRL for 3 vehicles, 4 vehicles, and 5 vehicles. It can be seen that Intra-FRL-WA provides favorable training performance and speed when compared with no-FRL for 3 vehicles, 4 vehicles, and 5 vehicles. Simulations are performed for no-FRL and Intra-FRL-WA for platoons of lengths 3, 4, and 5 vehicles across 4 random seeds. For all platoon lengths, Intra-FRL-WA was found to have the optimal performance. The simulation result for the 5 vehicle scenario is provided for Intra-FRL-WA versus no-FRL. In addition, the components of the reward equation, position error, velocity error, control input, and jerk are shown to be reduced to 0 very early in the episode, indicating a good selection of components in the reward and a strong convergence of the DDPG agents in the platoon. Finally, it is seen that Intra-FRL-WA provides better stability and more precise control across the system parameters when compared with no-FRL for all states, and especially in the position error of each vehicle in the platoon. An example of near optimal platooning is shown in this figure, where each vehicle is placed exactly on the flag of matching color. This is indicative of 0 position error in a platoon, for example. Now, where suboptimal platooning could occur, each vehicle could be slightly offset, indicating a position error in the platoon. Now, 2 simulations are provided here, and these are the simulations that corresponded to the figures on the previous slide for no-FRL and Intra-FRL-WA. It can be seen that Intra-FRL-WA in the bottom not only reaches the flags faster, but also tracks the flags more accurately, indicating better convergence than that of the no-FRL scenario, which drifts away from the flags as the episode continues. In conclusion, model weight aggregation was found to be the optimal aggregation strategy within Inter-FRL and Intra-FRL. In addition, Intra-FRL-WA was found to provide better performance than no-FRL and Inter-FRL. Last, Intra-FRL-WA was found to provide better performance than no-FRL for platoons up to 5 vehicles in length. In the future, the incorporation of weighted aggregation in the FRL aggregation method could provide performance benefits to the system. Furthermore, considering communication delays in the system model could make the system model more like the real world. Thank you for watching this video abstract for AVDDPG, Federated Reinforcement Learning applied to autonomous platoon control.